Awesome. Thanks everyone for joining us after the lunch break. Yeah, I'm really excited to talk a little bit about some of the recent experiments happening in our group on thinking about using the dynamics of decoherence as a way to look at the way that quantum information flows in a many-body system. This work, I think all of these folks are in the audience. This work was led in my group by Emily Davis, Bing Tianye, and Francisco, and has been a super fun, kind of a long time collaboration with Anya Jach and her graduate student, Simon Meinel, who are pictured here as well. We just posted the paper to archive a little while ago, so one can take a look here. Let me emphasize, actually, even before I start, that please interrupt me with questions. I'm going to try to go pretty slowly so that I explain at a very high level what the idea is. So please interrupt with questions. Don't necessarily save them for the end. Good. So I wanted to start getting everyone on the same page. So we're all familiar with thinking about decoherence. And usually the kind of conventional wisdom is that decoherence is bad for quantum computers. And we've heard a lot about that. You know, it limits how many cycles or the gate depth that one can get in different quantum information platforms. And as a general rule of thumb, the thing that, the plot that most experimentalists show when we think about decoherence is more or less to characterize some time scale. It might be the time scale for depolarization, which we typically call a T1 time scale. So when does the polarization of a qubit get lost? Or it might be the time scale for the loss of phase information, which we typically call a T2 time scale. But most oftentimes you see, experimental talk, there will be some discussion about decoherence that limits how long one can either evolve in time or the number of gates that one can do. And from these type of plots, the take-home message is simply a time scale that sets the fiducial value before which all interesting stuff must be done. And what I hope to tell you today is that maybe one can actually learn a little bit more by looking at plots like this than just the timescale beyond which things are dominated by so-called decoherence. And for that, I wanted to take the kind of maybe stat-mechy view of how to think about decoherence. And in particular, most of the time in often quantum devices, we think about decoherence as this single number because we're not interested in the environment. The environment is something that causes decoherence, but there's no sense in which it's sort of an interesting piece of the quantum system. But one might ask the opposite question, which is, what if the environment itself is an interesting many-body quantum system that one would like to explore in some non-trivial way? In this case, I'll probably almost certainly default to talking about spins because that's what the experiment will be talking about, but it's more general than that. Just think qubits in general, but my language will probably default to talking about spins. And what I mean from sort of this many-body viewpoint of decoherence is, imagine that you kind of have some spin degree of freedom, red here, that's storing some quantum information. And there's a many-body system of blue spins that's surrounding it. When we think about time evolution for this closed system, the time evolution entangles this red degree of freedom with all of the blue degrees of freedom. Just think time evolution under some generic high energy state. And then really we think about the loss of quantum coherence in a super simple way. If you trace out the blue spins, you find that you've lost all of the quantum information in red spins. But in some sense, this loss of information is just coming from interactions in this closed system. It's not, as long as the closed system you think about as being a part of your sort of many-body system and not as being some totally extrinsic environment. So the goal of the talk today is to ask the following question. If you imagine a probe qubit and the probe qubit is coupled to a strongly interacting many-body system, if you now look at the decoherence dynamics of the probe qubit, can those decoherence dynamics tell us something non-trivial or deep about the many-body dynamics of the system? I want to be very clear about what the flavor is. So let's be even more clear about the setting for the physics that we'll ask. The setting consists of the following three assumptions. We will assume that we have access to a probe qubit or a probe spin, and that this probe qubit can be fully controlled. We can do any operations we want on it, and it can also be read out. So we can figure out the quantum state of this probe qubit, and we can control it. And the picture that you want to keep in your head is that now there will be the dynamics of some many-body system in which the probe is embedded. And the dynamics of that many-body system, the fluctuations of that many-body system driven by something, will generate noise at the location of the qubit. The qubit will then feel that noise and decohere. Okay? So you have some dynamics of a many-body system. That's going to be fluctuations. I'm not going to be specific at this moment of what it's generated by, but we want to think about that as generating noise or many-body noise. And the question again that we're going to ask is, does the manner in which the qubit decoheres teach us something interesting? And I wanted to zoom in first into thinking about, the dynamics of the many-body system as noise. What exactly does that mean? I'll give a couple of pictures that hopefully give a feeling for that. We'll start imagining, for example, with a couple of examples. Let's start imagining that each of the constituent spins of this blue many-body system are driven by dynamics that are totally single particle, in the sense that the dynamics are not from coupling between these spins, but the dynamics are from this blue spin coupling to something else. So this, would be related, for example, to Avakar's talk from the first talk of today. Imagine if you had an atom undergoing spontaneous emission, then you might imagine that the field, in this case, I'll zoom into magnetic fields because eventually we'll talk about spins, but the field, for example, generated at the location of your probe qubit, if you're thinking about something like spontaneous emission, might look like, absorb a photon, jump up, emit a photon, come down, absorb a photon, jump up, come down. And this type of telegraph noise is very, very characteristic. It's kind of almost the definition of what you would get out of a master equation. And in that sense, it's precisely the physics of what conventionally in the master equation context is called quantum jumps, which if you've seen this PBS documentary, you are all very familiar with. So in this case, one could imagine that there's dynamics, from the blue spins, and these dynamics are generating a fluctuating field at the location of the probe qubit, and this fluctuating field takes the form of telegraph noise. One could imagine a slightly different scenario where one imagines that now, instead of the blue spin's dynamics being driven by, say, spontaneous emission or a master equation, let's imagine that we are literally incoherently driving this blue spin in some way, or even coherently driving in some way. And the idea here is, let's say, what you're really doing is that you start the blue spin on the north pole of the Bloch sphere. And in this two-level system, you apply a drive that kind of randomly kicks it around the Bloch sphere in some random way. And now if you looked at the noise that's generated at the location of the qubit from this particular kicked spin, you'd expect it to look very different. It's no longer a quantum jump. It's something you're literally moving around, maybe in even a coherent fashion. And here you would see basically that the noise generated there is now continuous, and depending on the nature of your drive, could also be totally Gaussian. And this would look something more like what goes under the moniker of something like Gauss-Markov noise. Okay? So just to give a flavor of what the basic idea is, there are dynamics in a many-body system. These first two examples are dynamics that are kind of single particle in some sense, but already give you a flavor that's at the single particle level, the dynamics and the noise that's generated by these dynamics can look very different. And the question that, one of the examples of the question, of the flavor of question that we'll be asking later on in the talk is, what happens if now the dynamics and the fluctuations of the many-body system are generated by intrinsic strongly interacting Hamiltonian dynamics? Could be gravitational, a la Greg, or it could be not gravitational, just some generic many-body system. It turns out this flavor of question has been asked, as one can imagine, for a long, long time. There's actually a really pretty paper by Clowder and Phil Anderson in PhysRev from the 1960s, which kind of gives what we think is the correct answer to this question. But I will hold off on answering it until a little bit later. But for now, I'll ask that each of you thinks in your mind whether or not, if you just have generic strongly interacting Hamiltonian dynamics driving the many-body system, should the noise that the qubit sees look like telegraph noise or Gauss-Markov noise? I tried to figure out how to do a poll in Zoom, but I failed. Otherwise, I would have done this poll. Okay, let's get into a little bit more of the details and the setup. The system that we're thinking about both from the theoretical side and the experimental side is what I would call a hybrid spin system. There are two flavors of spins in the system, and they're distinct. One flavor of the spin in the system is a probe spin represented here in red, and it will be coupled or embedded in a many-body system of other strongly interacting spins represented in blue. The total Hamiltonian for this combined probe many-body system is an interaction, HPS, between the probe and the system, and some interaction, Hamiltonian, between the constituents of the many-body system itself. Let me emphasize, I'm going to, to help you, I'm going to emphasize, we can think about, keep in mind a specific functional form for these two Hamiltonians, but actually the calculational framework is more general than that. But motivated by the experimental system that we'll see in just a little bit, we're going to assume that the system and probe interact with each other with a coupling of the form of a long-range power law, 1 over r to the alpha, alpha being the power law, Ising interaction. So the probe and the system spins do not exchange polarization, but they exchange energy via this Ising interaction. It's actually, in some sense, a very, very reasonable flavor of Hamiltonian that one has for lots of different AMO systems. But in our specific system, we're going to be talking about spins, and spins interact via magnetic dipole-dipole interactions. So in our specific case, this power law 1 over r to the alpha will actually be 1 over r cubed. Again, at this point, I'm not going to make any assumptions as I go through the theory about the form of the system's intrinsic internal interactions, but eventually the system will actually be governed by magnetic dipole-dipole interactions between the blue spins, just so you keep in mind what the physical system will actually be. So for those of you that are familiar, this will be a little bit of a review, but I want it to be very, very, very clear for those who aren't familiar with how I want you to think about decoherence. So when I say think about decoherence, the only thing I have access to in my experiments and in my theory is the probe qubit, is the coherence of the probe qubit. So when I ask about decoherence, I'm asking about what does the time dynamical decoherence of the probe qubit look like? And of course, there are two ingredients for this. The probe qubit is the one ingredient and noise is the other ingredient. So the way one often likes to think about decoherence oftentimes is in the sort of Fourier or spectral domain. And one often starts by thinking about what exactly the noise from the many-body system looks like. And the blue curve here is what I would call sort of a noise spectrum. And you can imagine it as more or less the noise that the qubit sees given Hamiltonian-driven dynamics of some many-body system. And the idea for sort of how this relates to correlation functions in the many-body system is super simple. In some sense, the intuition is that if you have many-body dynamics in the system of blue spins, you would look at what the spin-spin autocorrelation function is, I don't know, averaged over an appropriate temperature, for example. And the Fourier transform of the spin-spin autocorrelation function kind of gives the power spectral density of the noise, effectively this blue curve. Okay. And the probe qubit also must matter in some way. And the simplest way to think why the probe must matter is imagine that there's some intrinsic splitting between the two-level system of the probe spin. That means that the probe has to care more about noise at the frequency of the splitting than noise at other random frequencies. So in some sense, the qubit, the probe that is the qubit, also kind of filters the bare noise spectrum in some way. And those are the two ingredients, the only two ingredients I want you to take away from this plot. That there is some power spectrum of the noise. This tells you what the noise amplitude is at different frequencies. That is given in some deep sense by the autocorrelation function of the many-body system. And then there is some filter function that's imposed by the qubit, which tells you how exactly the qubit feels the different pieces of the noise spectrum as a function of frequency. And this particular filter function can be a high-pass filter. You can think about it, if you're engineering, think about it as high-pass filter, low-pass filter, and it will depend on the specific experimental sequence that you apply on the qubit to measure the noise. Okay, so lots of nodding, which is good. So let's be very clear about what exactly I just said that, it matters what the experimental sequence we do is. So let's be very clear in terms of specifying how exactly we measure decoherence, okay? So imagine that your probe is a two-level system, represented here as states 0 and 1, with some intrinsic splitting omega. Imagine that the first thing you're able to do is to push all of the population into the 0 state, so you're able to initialize the state of the qubit. Oftentimes, this is done in atomic physics, and certainly in our system optically. And the next thing you do is you apply a so-called pi/2 pulse. In the Bloch sphere picture, what this means is that you take the initial state, which is oriented in z on the Bloch sphere, and you push it onto the xy plane. Okay? So it's a superposition of 0 and 1 with some phase that would be defined in the xy plane. And the idea is that as the qubit now sees the magnetic field from the other spins from the many-body system, and as those magnetic fields now change, the qubit is going to have the probe qubit will have some Larmor precession and will sort of move around, will jitter around, and this phase is going to accumulate some phase relative to where it was initially when one did the pi/2 pulse. And this phase accumulation via interactions, via literally the Hamiltonian term, which was H probe system a couple of slides ago, is going to cause the qubit in general to accumulate a phase that's at sometime t, the integral of what the dynamics look like for each of the spin degrees of freedom in the many-body system. I here indexes the spin degrees of freedom, the constituent spins of the many-body system, the blue spins. And you repeat this measurement many times in order to build up statistics. And what you typically see is a decay of the coherence as represented here. And so now what I'd like to unpack a little bit is I'd like to claim that there's much more than meets the eye in terms of this functional form of this decay, in terms of this coherence as a function of time. And in particular, to unpack that, I'd like to emphasize that, in fact, there are two types of averages that naturally enter the coherence. And each type tells us something different about the many-body system. So first is what we call an average over trajectories, but there's nothing complicated about that. The naming trajectory, I think, is not actually super optimal. But the idea is that it doesn't have to be the case. One can replace this with a thermal average at some temperature. But in our specific system that we'll see in the experiments just a little while later, the many-body system starts off at infinite temperature. Okay? The splittings of the many-body system are very small relative to the temperature of the actual experiment. So for all intensive purposes, the many-body system is at infinite temperature, although one could replace this in the calculation with a density matrix at the right temperature. So there's an average. Since we're doing an infinite temperature average, if there are n spins in the many-body system, we're implicitly averaging over 2 to the n possible initial configurations because we have an identity density matrix. But what we're also averaging over are the subsequent trajectories, the subsequent dynamical trajectories driven by h int, the interaction Hamiltonian, of each of those constituent spins. And the idea is that if one's given some distribution of spin trajectories, these SZ I of t, then one will naturally also get a probability distribution for the phases that the probe qubit accumulates in the Ramsey spectroscopy, signal that I defined just on the previous slide. So there is a distribution of spin trajectories and thus a distribution of magnetic fields that is seen at the location of the probe qubit. And distribution naturally via the interaction between the qubit and these spins leads to a phase distribution that the qubit accumulates in such a spectroscopy experiment. When one averages over this phase distribution, you'll find immediately, super simple calculation, that the coherence looks like literally the average e to the minus I phi. This is the phase that's being accumulated. This e to the I phi comes from seeing what you get out, what you read out from a Ramsey experiment. And very, very, very often, you will see the assumption made via the equal sign here in red, where this is taken to be e to the minus phi squared over 2. And the second equality is true if the phase distribution is Gaussian. Okay? And for lots of reasons in different settings, you can get Gaussian phase distributions. As we will see, this is not always the case. But in those cases where it is true, this equality is exact. And if the coherence now, so let's kind of implicitly make that assumption for a second, and then we'll come back to sort of post-rationalize it. So if we make that assumption, then we're thinking about what the expectation value of this phi squared is. We remember phi itself has SZI of t. So phi squared expectation value, as I promised you, will naturally have correlation functions, 2-time correlation functions of the spin degrees of freedom of the many-body system. So this will exactly be kind of where the autocorrelation function enters. And in particular, phi squared will know about something which we call chi over here. And the chi is precisely the object that I showed in a previous slide, where chi will know both about the power spectrum of the noise, and that's via the fact that it knows about the spin-spin autocorrelation function, precisely because phi squared has 2 SZI of t's. And it will also know about the filter function imposed by both the experiment and the structure of the qubit. Okay? So there's 2 things that enter chi, and those are the 2 things that I wanted you to keep in mind for the very first plot that I showed. It knows about the noise spectrum, S of omega, and it also knows about the filter function imposed by the qubit. So just to give you a little bit of intuition, that in fact, the nature of decoherence should in fact tell us certain things about the many-body system. We can already gain some intuition that if the dynamics of the many-body system driven by the Hamiltonian, for example, has some natural correlation time to it, that the nature of the decoherence should definitely change at that correlation time. And more or less the correlation time, it's very simple. If you have some typical interaction scale that lives in H int, the Hamiltonian that describes the many-body system, then more or less that correlation time you can kind of think of as being something like 1 over that interaction strength. Okay. And the way to think about this is then, the nature of why the decoherence changes is very simple. If you're at very, very short times before the correlation time, then the system spins are static. If you're at a time scale much less than 1 over j, where j is the coefficient of the interaction strength of h int, if your time goes much less than j, nothing's happened. There's no flip-flop dynamics in the system, and that means that the spins are kind of static in the many-body system. And this means that your sort of phase accumulates ballistically. It doesn't sort of accumulate in kind of a random walk fashion. And that ballistic accumulation, you immediately find that chi, this object that knows about both the noise spectrum and the filter function, scales as time squared. On the other hand, if you're at late times, if you're at times much larger than the correlation time of the many-body dynamics in the system, then many spins have flipped, and this means that the phase kind of jitters back and forth. Sometimes you'll see a positive phase, sometimes you'll alarm or process in the opposite direction, and that means that the phase will accumulate as in a random walk, and here chi will scale as time, linearly in time as t. The bottom line is that when we consider this kind of average over trajectories, that the average over, that this average gives us a coherence, a signal that more looks like a decay, e to the minus interaction squared, chi, which knows about the noise spectrum and the filter function, and some power law that comes from the fact that we originally had a power law in the interaction between the probe and the system. Okay. But at the end of the day, kind of the most basic theory of decoherence that you find in any textbook, the coherence knows about e to the minus chi. Chi has a noise spectrum in it and also a filter function. So it turns out that actually, again, kind of motivated by the experimental system, that there's a second average that I'll make here. It doesn't always have to be there, and one can do the calculation without it. But the second average that's kind of motivated by our experimental system is an average over randomly positioned spins in space. And you can already kind of see that I've used the word position here. And indeed, the second average will teach us something about the real space structure of the many-body system. In the same way that the first average, at the end of the day, we know something about the autocorrelation functions of the many-body system, so we know something about time dynamics. The second average will teach us something about the real space structure of the many-body system, and that's because we're averaging over positions in some non-trivial way. The assumptions that I'm going to make here are twofold. The first is that the spins in the many-body system, the blue spins, are going to be randomly positioned in space. And the second assumption is that I'm going to get to look at many different probe spins. So the probe spins will still be extremely dilute relative to the blue spins. The red probe spins will still be extremely dilute relative to the blue spins. But in an experiment, I'm going to average over multiple of these red probe spins. So for each red probe spin, it sees some local environment of a strongly interacting many-body system of blue spins. But for another probe spin, you also see the same thing at 10,000 feet, but if you zoom in locally, it will have a different distribution of locations for these blue spins relative to where the probe is, and that average matters. Okay. And what you'll find, without going into very much detail, is that when you now do the spatial average, the coherence will still be almost the same form as what we had in the previous slide, except now the coherence will take the form of chi, which knows about the noise spectrum, the Fourier transform of the autocorrelation function, as well as the filter function, but it will also be taken to a power d over 2 alpha, where d is the dimensionality of the spin system, the effective dimensionality of the spin system, and again, alpha is the power law of the interaction. And the fact that the dynamics of the spin degrees of freedom know whether or not they are in D equal 1 dimension, 2 dimension, 3 dimension, gravity, infinite dimension, all coupled, is precisely coming from this positional average, is implicitly coming from this positional average over here. So what's the expectation? The theory expectation is that if you look carefully at the probe's decoherence and you don't ask for just a number, but you looked at the structure of the decoherence, that actually it looks like a stretched exponential decay. And my claim is that the best way to see this stretched exponential, to see the structure of this, is first to log this coherence. If you log the coherence, you take away the E, then take a negative sign of that. So you take away the negative sign over here, and now you just have a power law, right? So if you first take negative log C of t, now you just have a power law that looks like some function chi of t to the d over alpha. So that's a power law. And if you want to see power laws, you should plot it on log plots and look for lines. That is what you learn in 3rd grade. So the point is that the way we're going to do this is we're going to take the negative log of the coherence signal and then plot that on a log plot. And what you should expect to see in theory is this. Okay, so I mean, this could be sort of negative log of C of t. I mean, it's equivalent to log of phi squared, but I'm just converting from phi squared to c. Because c, remember, was e to the negative phi squared over 2. So that's exactly what I'm doing here. So there's a couple of features of this prediction that are kind of very nice. So it turns out, as promised, depending on what type of experimental sequence you measure the decoherence with, you might see different things. Let's focus first on this kind of case that I explained, Ramsey. So this pi over 2 pulse with no additional stuff. I said that at times before the correlation time and at times after the correlation time of the many-body system, you expect to see something very different. And in particular, the prediction is that you see a stretch exponent, or here a power law that looks like d over alpha in a Ramsey spectroscopy decoherence experiment before the correlation time, and d over 2 alpha for times after the coherence time, after the correlation time. Again, d here is the dimensionality of the sample of the system, and alpha is the power law. A different filter function, a different experimental sequence called spin echo, will give you something slightly different for the early time behavior. And as a general rule of thumb, it can only give you something slightly different for the early time behavior. And the reason for that is that if you're at a time scale after the correlation time, no matter what pulse sequence you do, there's been many flip-flops. So you're not really going to be canceling anything out in addition with different pulse sequences. So the expectation is that beyond the correlation time of the many-body spin dynamics, all pulse sequences will lie on this d over 2 alpha line. But before that, spin echo will actually give, under a Gauss-Markov noise assumption, 3d over 2 alpha. Okay, so these are the kind of predictions here. And so let me now just jump a little bit into the experimental system that we're looking at. The experimental platform we look at is indeed a hybrid spin system. It corresponds to 2 types of coupled spin qubits in diamond. A diamond is naturally a 3D material. And the 2 types of defects, the 2 types of spins, are NV centers. The NV centers are the red probe qubits, and P1 centers, the P1 centers are the blue strongly interacting many-body system. Okay. We will work with a magnetic field such that the energy levels of the probe qubit and the energy levels of the strongly interacting spins are very strongly off-resonant relative to their intrinsic interaction. So there will not be any resonant flip-flop dynamics, and that's precisely why in the original, one of the original slides, I assumed that the probe system coupling was just an Ising interaction. And we will work with samples where the probe has a density in the diamond lattice of less than 1 part per million, and the many-body system has some density between 10 and 100 parts per million. So indeed, you will have very dilute probes surrounded by strongly interacting many-body systems. Okay. And again, let me just emphasize one last time that the many-body dynamics between the blue spins at their intrinsic core are driven by magnetic dipole-dipole interactions. But again, because there is a magnetic field applied, even those magnetic dipole-dipole interactions between the blue spins have terms that don't conserve energy. So if one restricts to energy conserving terms, because the interaction strength is much weaker than this magnetic field-induced splitting, then one naturally gets a long-range XXZ model that describes the dynamics between the blue spin degrees of freedom. You have long-range flip-flops, S plus, S minus, and long-range IZ interactions as Z as Z between the spins. Okay. Not super important, but just to emphasize that kind of we have an experimental platform that really sort of mimics the setting that I tried to explain in the very beginning. And I'll just emphasize that, you know, kind of from the theoretical expectation that we had, some dimensionality sort of entered in some very, very nice way. So one of the easiest ways just to kind of look at these types of decoherence dynamics is to look at different dimensional systems, same NVP1 system, so same spin system, but now just two different experimental samples. One of the samples, which is grown by Anya's group, has a very, very thin two-dimensional layer of spins. And the sort of fiducial marking that it's 2D is that the average spacing between the spins is larger than the thickness of this layer. So that now there's one direction where you think about the spins don't see anything in the other direction. So the average spacing between spins is larger than the thickness of the layer, and we should expect that effectively in this type of a sample, one gets two-dimensional dynamics. Actually, the sample itself is super cool, but it's hard to get, but I won't emphasize too much. And there's more conventional samples where one has a three-dimensional lattice of these types of spin degrees of freedom. One can measure the decoherence dynamics in both of these, and one of them corresponds to 2D, and one of them corresponds to 3D. And if I asked you which one corresponds to which, it'd be very hard for you to say which one corresponds to which. In fact, they both generally look like they're kind of decaying. And it's, in fact, actually the blue data is actually the two-dimensional sample, and the yellow data, the gold data, is the three-dimensional sample. But from this, you know, it just looks like it's some decaying function. The coherence is lost as a function of time, somewhat unsurprising. But let's now think carefully and replot this data in this negative log in a log-log plot. And what one sees is something super, super pretty. So forget the gold data and start with the two-dimensional blue data. The expectation is that in 2 dimension, you should see a stretch exponent that goes from 2/3, because alpha is always 3 because you have dipole-dipole interactions, but the dimension is 2/3 to 1/3. And in fact, again, this is a log-log plot where we're plotting the negative log of the coherence. You, in fact, for the two-dimensional sample, really do see at least a decade in the 1/3, maybe almost a decade in the 2/3, but a solid power law that shows that it's kind of 2/3 at short times, 1/3 at late times. And this immediately allows you to actually, just by looking at where they kink, identify what the many-body correlation time is for the P1 spin system, for the strongly interacting system of dipoles. If you do the same thing on the three-dimensional plot, on the three-dimensional sample, you'll actually see that now D over alpha is 3 and 3, so you should expect 1. And indeed, over, again, at least a decade in time, it's pretty consistent with the stretch exponent being 1. It turns out that remember that the fact that this number is bigger than this number means that your coherence is decaying faster. And the reason we can't see the crossover to 1/2, which would be the expectation post-correlation time, is that it decays so fast that we're kind of at the noise floor here. So it's very, very hard to make out a signal after that. But indeed, looking at more than just a time scale, but at the actual profile of the decoherence, even if you knew nothing about the sample, you can immediately tell whether or not the effective dynamics of the spin system, they think they're in 2D or they think they're in 3D. For kind of optical lattice experiments like we're hearing about or tweezer experiments like we were hearing about in Avakar's talk, this question is maybe a little bit obsolete because you make your optical lattice or your tweezer to be in whatever dimension you want. In the solid state, it's much, much harder to ask what the effective dimensionality of an interacting spin system is. So this is, I think, much more important there.
You have 10 minutes.
Sorry?
No, you have 10 minutes.
Fantastic. Yeah, good. Okay, I'm almost sort of towards the end. So the second thing we can do, I sort of identified this correlation time already at the kink of kind of this transition from early time ballistic behavior to late time kind of random walk behavior. But I'm just emphasizing that literally looking at decoherence carefully, in this case, would tell you what the effective spin dimension is for the system. One can actually also control the many-body correlation time. So now we're moving away from this picture where the spin dynamics of the many-body system are driven by intrinsic interactions, and we're going to put extrinsic driving onto the spins to try to shorten the correlation time. And when you do shorten the correlation time, just as a remembrance, another way to see what the correlation time is where these two different types of spectroscopy experiments overlap. And when we turn on this external drive to shorten the correlation time, you can exactly see that the position where these two different pulse sequences, in this case, Ramsey spectroscopy in blue and spin echo spectroscopy in red, the point where their overlap gets shorter and shorter in time, precisely coming from the fact that we are driving with an incoherent drive where the correlation time of the drive is getting shorter and shorter. So when that begins to dominate the many-body dynamics of the system, then the correlation time of the spin system is inherited kind of from the correlation time of the incoherent drive, and that causes it to shorten in this way. Just shows that we can have sort of external control over this correlation time in a very simple way. So let's turn to ending on kind of ending on something I think is quite interesting. Something I emphasized that was relatively subtle is whether or not we should think about the noise that's generated by a many-body dynamical system, a strongly interacting many-body dynamical system, as looking like Gaussian or Telegraph. And in particular, I emphasize that even the assumption that the coherence time takes the form of this e to the minus phi squared is implicitly making a Gaussian assumption about the phase distribution. It turns out that we didn't just look at multiple spectroscopies because it was nice to do. It turns out these different types of spectroscopies have different powers in terms of discerning this type of physics. And depending on whether or not one has Gauss-Markov noise or Gaussian noise or telegraph noise, the spin echo spectroscopy should show a different stretch exponent in the early time behavior before TC, before the correlation time of the many-body system. In particular, let's just focus on the 3D sample. In the three-dimensional system, Gaussian noise would give you D is 3, alpha is 3, so it would give you a stretch of 3/2. And telegraph noise, which is 1 plus D over alpha, would give you, oh, I can't add. 3 over 3 is 1, and 1 plus 1 is 2. I'm sorry. This should actually be a stretch of 2. So it turns out that this classic paper that I mentioned from Clowder and Phil Anderson back in the 1960s said that if you have, or was consistent with the idea that if you have a generic many-body system strongly interacting, that you should actually see telegraph noise. So you can, those of you that said telegraph noise back on slide 2 can pat yourself on the back, and those of you that were like me and thought it should be Gaussian can wonder. So the intuition for why it should be telegraph noise is super simple. Kind of comes from the intuition of StatMech. The idea is that each individual spin, each individual blue spin in the many-body system sees the other blue spins as a bath, So you'd like to basically write down a master equation for this when you trace out the mass for this single blue spin, and thus that single blue spin should undergo something that more or less looks like quantum jumps. So we would expect actually that the spin echo signal that we see for this many-body system, in fact, looks like telegraph noise and looks like has a power law of 2. This is the data. I would claim that the spin echo signal, again, log as a function of negative log of the coherence, it looks very, very clean 3/2 behavior. Maybe a little bit more than a decade in time, but certainly discernible from 2. No question that a power law of 2 would not fit here. So it turns out that in the probe qubit is seeing noise that's consistent with with each of the spins of the many-body system as generating telegraph noise, as opposed to something that looks like Gauss-Markov noise. And it's honestly not super clear to us why this is the case. We have some conjecture. We think it might be because of the amount of disorder that kind of exists in the system. So the many-body dynamics are not actually scrambling very quickly in the blue spins. But the fact that we see this kind of telegraph noise as opposed to Gauss-Markov is something that we're still pondering. And certainly if folks in the audience have thoughts, we'd be very interested in hearing about it. My time is basically up, and I definitely don't want to interrupt the poster session. So let me just emphasize again that this has been just a really tremendously fun and wonderful collaboration with Anya's group, and that on the experimental side, it was led by Emily Davis and Thomas Mittiga, and on the theory side, we had some wonderful, wonderful calculations from Bing Tian and Francisco. And with that, let me thank you for your attention.
Thank you very much, Noah, for interesting talk. We have 3 minutes for questions.
Sorry, Norman, I still don't quite understand the intuition why it's a telegraph rather than Gaussian.
Yeah, so the logical flow, as far as I understand from kind of back in the day, is that you had this closed system of strongly interacting spins, and you take a single degree of freedom, and the reason why it thermalizes, or the reason why ETH works, is that you can think about this degree of freedom as thermalizing because the rest of the system behaves as a bath for this degree of freedom.
Yeah.
So with that logic, you maybe can then write down naturally a master equation for the dynamics of this. And the master equation, all it cares about are kind of 2-point correlation functions of the bath. And if you can write down a master equation validly for this spin degree of freedom, then the master equation immediately tells you that all you have are quantum jumps. And once you have quantum jumps, then you know that the signal has to look like a telegraph.
But the full master equation is an average of those quantum jumps, right?
Yep. Exactly, that's right.
Isn't it true that when I take that average, can't I write that resulting master equation in this Ito calculus or stochastic? It looks like a stochastic.
In general, your intuition is absolutely right, but your intuition is taking you beyond the correlation time. So usually, you think about the master equation and you think about the bath as having a correlation time, and that's TC. And all of the stuff, when the master equation, what you like to do,
I see.
You like to evolve for times longer than TC, but less than something where errors happen.
That's right. We like to take a Markov approximation where this TC is tiny.
But I'm emphasizing that the place where this distinction appears in sort of whether it's telegraph or Gaussian noise is before TC. And it literally comes from whether or not, like, this distribution, like, remember the SZI of T, like, whether it's it comes from whether or not the higher order moments, SZI of T1, SZI of T2, SZI of T3, SZI of T4, whether or not those factorize or not. In the Gaussian case, they do factorize, and in the telegraph case, they do not. And the fact that they don't factorize matters for things before TC, and is why Echo knows about it.
I see.
So it's like a crossover. So there is like a crossover from telegraph to
yeah, sure. Right, you can think about it that way. I guess yes, exactly. And maybe the way to think about it is after TC, everything's kind of Gaussian. Before TC, you can kind of know that things are sort of, telegraph or non-Gaussian. And then at TC, sort of, you cross over to this kind of average, this average picture that Greg was sort of mentioning. But yeah, that's right.
Doesn't it depends on the number of qubits in the bath? Because it's a sum over all these SZIs. And if I use like the law of large numbers, those will approach to a Gaussian.
Yeah, so that's the point. Actually, you can. That's right. I mean, you would think that. So that again, that intuition is true after TC actually. So you can try to do. You can literally try to take a process like this and average and see that the law of large numbers before TC will actually not get you that Gaussian and will actually look like a Lorentzian actually. So the phase distribution that you get out will actually, well, it's actually not always Lorentzian, depends a little bit, but it will not be Gaussian.
I see.
And again, at some deep level, it relates to whether or not you're looking at time before or after the correlation time.
And again, this correlation time, we should have in mind, that the many body system is a chaotic scrambling system, right? So this TC is.
Yeah, that's right. That's right. No, that's right. No, I actually I've asked Emily this question. She hasn't provided a sufficiently useful answer yet. But what exactly happens if you have a localized behavior? So, or something that's subdiffusive, for example, or very slow.
Right, exactly.
But in general, I'm making the implicit assumption that the system will be chaotic, and that I think that if you're localized, probably in some deep sense, you actually maybe should expect something like this. And the reason for that is that if you're localized, basically, there's not so much spreading or scrambling of this information. So in some sense, there's no real sense in which the system behaves as a bath for itself. So that kind of the master equation doesn't look very good. So it's really like, more or less coherent, evolution between a couple of a very small set of very strongly coupled network of spins. And within that, maybe 2 to the 3, 2 to the 4 spin Hilbert space, then you still will see something that looks very Gaussian and continuous.
I guess another question on that is what would happen? Of course, you don't have free fermions in your NV center, but what happens if your bath is free fermions?
Okay, I have not thought about that question, but I'm sure I'll be able to answer it. Let me think about it.
Or some other, free particle.
Bath is free fermions. Yeah, okay, so maybe I can't, because I have to be a little bit careful. I mean, like we have to define what exactly, HPS is. So, okay, so you could imagine, for example, that you have a one-dimensional transverse field Ising model that is free. We know it's free, but we can imagine that now the spin interacts, our probe spin interacts with this one-dimensional thing. And actually, I don't really know whether or not the freeness matters. Like at some level, I mean, like you still have, let me think about this. I guess, yeah, I don't exactly know how to think about this, because in that case, you can have dynamics, but you have, maybe it matters. I guess, yeah, I think it matters. Okay, so let me say this. So if it's free, like truly non-interacting and free, maybe again, there's some sense in which you couple to degrees of freedom that kind of don't really spread in some way. And thus you should expect things that are kind of local and not behaving as baths for itself. And that would maybe be more Gaussian. But I think that if you had a system that was integrable, like what Roman was saying, integrable but interacting, I don't think that you would be able to distinguish that from something that actually scrambles, at least from the decoherence of the probe qubit. I'm not 100% sure, but I think that's probably the case. But in the free case, in the truly free non-interacting case, I think maybe you would indeed, it just wouldn't thermalize in the same way, because there would be no scattering between excitations in the transferialized model. Although, of course, if you want to do things self-consistently, there are interactions between those degrees of freedom in the bath mediated by interactions with the probe. So at some time scale, maybe you expect a crossover in some way.
Okay, cool. Thanks.
Okay, let's thank Noam again.